In the heart of California, the Oroville Dam stands as an immense feat of engineering, the tallest dam in the United States. For decades, it reliably managed the state's precious water resources, a symbol of security and control over nature's powerful forces. Its massive reservoir, Lake Oroville, held back billions of gallons, supplying water and generating power for millions. Yet, beneath this veneer of strength, a hidden vulnerability festered, a design flaw that would, in the winter of 2017, transform a critical infrastructure component into a raging destructive force, threatening catastrophe for all downstream. At the core of the dam's flood control system was its main spillway, a monumental concrete chute designed to safely release excess water from the reservoir. This reinforced concrete structure, stretching over 3,000 feet, was engineered to withstand the immense hydraulic forces of high-velocity water. Its purpose was clear: to prevent overtopping of the main dam during periods of heavy rainfall and snowmelt, ensuring the controlled flow downstream and protecting communities below. It was a crucial safety valve, built to endure the most demanding conditions for decades. February 7, 2017. Following an exceptionally wet winter, the main spillway was operating at significant capacity. It was then that a gaping hole, roughly 250 feet wide, was discovered in the concrete chute. This wasn't merely surface damage; a high-velocity water had punched through the reinforced concrete, exposing the underlying earthen embankment. The incident immediately raised alarms, but the full scope of the structural degradation and the relentless hydraulic forces at play were only just beginning to reveal themselves. The spillway's integrity was compromised, and the situation was rapidly deteriorating. The failure wasn't a sudden collapse but a progressive assault by water. High-velocity flow, reaching speeds of over 50 miles per hour, exerts immense pressure, creating a phenomenon known as cavitation, the formation and implosion of air bubbles that literally chip away at the concrete. This, combined with abrasive forces from debris within the flow, quickly breached the protective concrete layer. Once the armor was compromised, the water found paths underneath the remaining structure, beginning the catastrophic process of structural undermining, accelerating the damage exponentially with each passing minute. As the concrete chute continued to disintegrate, the underlying native bedrock was exposed to the same relentless, high-velocity water. This bedrock, initially believed to be stable, proved susceptible to hydraulic plucking and scour. The intense flows began to carve massive channels into the geological foundation beneath the spillway, accelerating the collapse. This wasn't just erosion of the chute, it was the active dismantling of the very ground upon which the spillway rested, threatening to destabilize the entire structure and, by extension, the integrity of the dam itself. With the main spillway severely damaged and the reservoir rapidly filling, authorities had no choice but to activate the dam's emergency spillway. Unlike the main structure, this was a simple concrete were designed to allow water to flow over an unlined hillside, relying on natural topography to guide the water away. It was intended for rare, extreme events and had never been fully tested. The geological assessment preceding its original construction had not adequately accounted for the erosive power of high-volume, turbulent water directly on the natural ground. This oversight would soon become glaringly apparent. As water poured over the emergency spillway, the unlined hillside began to erode at an alarming rate. Massive chunks of earth and rock were stripped away, creating a deep gully that threatened to undermine the concrete weir itself. If the weir failed, an uncontrolled torrent would cascade down the hillside, potentially eroding the ground around the main dam and leading to a catastrophic collapse. The danger was so immense that on February 12, 2017, an immediate evacuation order was issued for nearly 180,000 residents downstream, fearing a complete breach and a wall of water. Panic gripped the region. Engineers and emergency responders launched a desperate, round-the-clock effort to avert disaster. Helicopters continuously dropped massive quantities of rock and aggregate into the eroding emergency spillway channel, attempting to stabilize the hillside. Controlled releases from the main spillway were carefully managed to lower the reservoir level, reducing pressure on both damaged structures. It was a high-stakes battle against time and the relentless power of water, a monumental display of human ingenuity and resilience pushed to its absolute limits to protect lives and prevent an unimaginable disaster. The Oroville Dam crisis served as a stark, undeniable wake-up call for the entire nation. It exposed the critical need for comprehensive geological assessment in the design and ongoing maintenance of aging water infrastructure, particularly concerning spillways and their underlying foundations. The event highlighted that even the most robust engineering can be vulnerable without thorough understanding of subterranean conditions and the relentless forces of high-velocity water. Oroville stands as a powerful reminder that proactive investment, meticulous inspection, and continuous re-evaluation are not luxuries, but essential requirements for public safety.